Hello there. In this video, I'll be talking about how rotations actually work in Game Garage, how to angle any object to a specific orientation that you want, as well as how the angle sensor actually works, and how do these outputs of the angle sensor actually relate to the rotation settings that we have in all of the objects. So let's begin. So you're probably already familiar that there's three different rotations available in Game Boy Garage. There's X rotation, Y rotation, and Z rotation. So these three rotations are based on the three axes of the world. X goes from left to right, Y goes from bottom to top, and Z goes from back to front. Now, how do these three different axes relate to the three rotations that are in the game? So an easy rule to use to figure out what direction a certain rotation is to use something called the left hand rule. So the left hand rule, for example, let's try to figure out what a X rotation would look like. So if we're using the left hand rule, you take out your left hand, you open your palm, point your left thumb towards the positive axis. So in this case, we're looking for the rotation of X. So we know that the positive X is to the right. So we point our left thumb to the right. Then if you try to close your fist and roll up your fingers, the rotation of your fingers will be the direction of the rotation. So let me just show you here. If our thumb is pointed to the right here, and we try to close our fist, you'll notice that the rotation of our fingers will go around like this. So this is the x-axis, and an x rotation will go around like this. The same thing happens for all the other axes. For example, for the y-axis, using the left hand rule again, you point your thumb upwards. Then if you try to close your fist, you'll notice that the rotation of your fingers will go around like this instead. So now you can see that it goes around the y-axis here. And as for the z-axis, it's the same. The z-axis points straight into the screen. So you point your thumb into the screen, try to close your fist. You will notice that it will rotate counterclockwise. And that's a simple way of figuring out the rotation of each axis. Now, how do we use this to angle our objects in a specific way? Let me take an example here. Here's just a normal object. And I'm going to try to angle it in a specific way. So let's say if we try to rotate its x-axis around by 45 degrees, and we know that the rotation of the x-axis will be like that. So we know that if we rotate it around by 45 degrees, this thing is just going to rotate this way 45 degrees, and we'll end up with this. You can see here, exactly the same. The same thing for every other axis. For example, let's say we rotate this by 30. We rotate this object around the y-axis for 30 degrees. See, like that. Lastly, for the z-axis, just to show you, say negative 120, it will rotate the object clockwise by 120 degrees, like that. Now, most of the confusion comes when you try to rotate an object using multiple angles. For example, what if you try to rotate an object, let's say, let's keep the negative 120 degrees and rotate it like 45 and then 15. When we look at the object, it kind of makes less sense how an x rotation of 15, y of 45, and a z of negative 120 would end up like this. So here I'm going to try to explain to you how you can more intuitively figure out what these rotations here in the settings would result in the actual game. So one key thing to understand here is that the game actually has a very specific order in which it rotates the objects. So let me show you step by step how the game actually ended up with this rotation. So the order that the game actually rotates objects is from Z and to Y and to X. Now remember, Z rotation is the rotation around this blue arrow here you see off screen. Y rotation is rotation around the green arrow, which is the y-axis of the object. And X rotation is rotation around the red arrow of the object, or its x-axis. So if we try to replicate the rotation of this object with that in mind, we'll see that okay, it's negative 120, 45, and 15. You first rotate the object negative 120 in the z-axis. See, it's going to end up here. Now, if we try to rotate the object in its y-axis, you'll see that now the object will rotate around its y-axis here, the same direction as shown here in this diagram. But now, since we rotated the direction of its y-axis pointing towards here, now the rotation applied by changing this y-axis setting will now make the object rotate around this axis and not this axis. So there we set it to 45. Then lastly, if we try to rotate it in the x-axis, well, now the x-axis, if you recall, is the red arrow here. It will now rotate around this arrow and not how we naturally understand where the x-axis is. And you'll see that it will rotate around like that. And if we set this specifically to 15 degrees, like we set in our settings, you'll see that it will end up in the exact position that we saw earlier. Now, for some people, me included, keeping track of where these axes of the object are whenever you try to rotate it is pretty difficult to do in your head. So thinking of these angles in this way might be a little difficult to visualize. So here's the alternate method which I use to try to figure out how rotations are done. If you view it in the order of x, y, and z, now all you need to pay attention to is the rotation that you can see here in the bottom left. So rotation around the primary axes of the world. So let me show you. So first with the rotation with the x, that's still normal since we haven't changed anything. I just set that to positive 15. Now next, if we're going from x, y, and z, we don't need to keep track of these three arrows anymore, and you just need to remember where the y-axis, x-axis, and z-axis in the world is. For example, here, if we want to rotate it across y, you can see that the object will now rotate around the world y-axis. So it will rotate the exact same way as you can see here in the bottom left. And now if you set this to 45, it will go on there. And then if we try to rotate it around z, it will now rotate around the world's y-axis instead. You'll see if we try to rotate it positively, it's going to rotate like that. And if we set it down to negative 120, we're going to end up with the same configuration as before. So what I'm just showing you here are different ways to think about how the objects end up at these angles. We're not changing how the angles are actually implemented into the game. Regardless of what order you input these values in the settings, it's always going to end up in the same orientation. I just showed you two ways of trying to more intuitively understand how we end up from this base rotation to the final rotation that we had when we have all three settings inputted. Now, before we go into how angle sensors actually work, let me just explain how and when do these rotation settings actually work. So here, you can see here, if an object is on its own, whatever rotation that we set here will be applied to the object at the very start of the game. Now, what happens if we connect our object onto another object? So here, for example, we have two objects here. Now, if we try to rotate our first object here, it's going to be rotated like that and connected to this other object. You'll notice that the object goes back to its original rotation. Now, this all depends on how the connection settings are set. So in this example, the connection point is set to center center. So if the connection point is set to center center and the object is connected on top of another object, anything that you put here in the rotation settings will be ignored. So regardless if I change all of these to like a different value, whatever rotation that the bottom object has, this object will copy that rotation. Something interesting happens when your connection point is not center to center. So let's say we set it to y minus to y plus. See here, y minus is connected to the y plus of the bottom object. We can try setting our y-axis to 90 degrees, and you'll see that the object actually rotates. So if the connection point is anything but center to center, it will be able to rotate, but only for a certain few values. For example, here we have 90 degrees. You can also set this to 180 degrees and also to negative 90 degrees. So those four values work. However, when I set any value besides any of those four values, let's say 20 degrees, you will notice that the object goes back as if all of its settings are set to 0. So what's happening here is that if your object is connected on top of another object, whatever rotation that you set here, it will just round to the closest 90 degrees. Just to illustrate that, in this example, I set this to 20 degrees. So 20 is in between 0 and 90, but it's closer to 0, so it's going to round to 0. If I change it to something like 70, now 70 is much closer to 90 than is it to 0, so it will be rotated by 90 degrees. Same thing for the other values. Let's say I set this to 160. 160 is closest to 180, so this will be rotated by 180. And if I set this to like negative 70, this is closest to negative 90. So that is how rotations work when you have objects connected to them. But now let me show you something peculiar. Well, this y-axis rotation work. Now what if we change the different rotations? Like for example, the x-axis. Set the x-axis to 90. Notice that the object does not rotate at all. Or if we set this back to 0 and set the z-axis to 90, you will notice that the rotation doesn't work either. However, if I set both x and z-axis to 90, see what happens. The object, for some reason, changes its rotation. So what's actually happening here? So here's how the game actually connects objects that are rotated. Let me disconnect this first and show you what the rotation of this object looks like. So here's an object with the x rotation of 90 and z rotation of 90. You can see here its y-axis is now pointing into the screen. So the negative y-axis is what we're seeing here, and the arrow is at the back over there pointing into the horizon. What the game does is that when you try to connect multiple objects together, what it will first do is initialize whatever rotation that you set to it. And then starting from that, it then tries to connect the connection point of this object onto the object you're connecting it to. So let me go back to a simpler example first. So in the example where we had a y rotation of 90, you can see here that, well, this is the negative y face of this object, and this is the positive y face of the object. So what the game did is that first it rotated this object by 90 degrees in the y, and then from this position, it tries to connect this object, this negative y, to the positive y of this object. So that's why when we connect this here, these two objects are connected this way, while this thing is still rotated. Now, if we do something like setting the z-axis rotation to just 90 and 0 on everything else, you'll notice that the object will now be rotated this way. Now, what will happen if we try to connect it from y minus to y plus? Well, the game will see that the y minus face of the object is over here, and the y plus face of this object is over here. So since the setting is set to y minus to y plus, it basically just forces this face to be connected to this face. So the easiest way for the game to do that is to basically just rotate the object like this. So like right now it's like this. It wants to connect this part of the arrow to this face of the arrow. So these two faces need to be aligned. So what it does is just simply rotates the object like that. And you can see that when we connect these two, that's exactly what happens. Basically rotated this point to face exactly the face of this point. Now what happened when we set both x and z to 90 degrees? Here you can see that when x and z are set to 90 degrees, the arrow part of the y-axis is now pointing into the horizon, and the negative y is what we're seeing here facing us in the screen. So now imagine from the game's perspective, if you just want to connect this base of the object onto this arrow, well, all it would need to do is just take this base and just basically rotate it like that. So right now, let me show you. The negative y arrow is like this. So there's the negative y. So if it wants to connect this face to this face, the game will do is rotate it down like that. But since the specific rotation of x and z rotated the object in such a way that now the blue arrow is now pointing to the right instead of the red arrow, well, when the game connects this face to this face, that's how the object gets connected. And just to further illustrate the point, let's say we have this certain rotation. So if we want to connect the x minus of this object, which is this part of the arrow, to the y plus of this object, well, that's very simple. The game just needs to connect these two. And if we do that, say x minus to y plus, yeah, if we just connect that, it's just going to get connected like that. Now, if we change the setting to be like x minus to the x plus of this, what the game will do now is basically rotate this thing to make sure that this face is connected to this face. It will just rotate this thing like 90 degrees that way and connect this part to this part. And you can see if we do that, so x minus 2x plus, it will do exactly that. The same thing happens even if both objects are rotated. So let's take this and rotate this by 90 degrees in the z-axis. You'll see that the x-axis of this is now pointing upwards. So if we say connect the negative x of this object to the positive x of this, it will just connect those two accordingly, like that. But if we try to connect like the negative x of this object to the negative y, well then this will just rotate 90 degrees like that and connect this face to this face. You can see negative x to negative y, it connects like that. And if I set it to like negative x to positive y, it's just going to connect, rotate the other way, and connect like that. So that's basically how the game handles connections and rotations. Now this next portion of this video is going to be dedicated to understanding the angle sensor. So here we have the angle sensor, and I've connected the angle sensor to this object that we're looking at here that's connected to all of the hinges that I'm able to control with this setup. So if you've ever played with angle sensors and setting their rotations manually, you would know that if you set just one angle of the object, the output of the angle sensor will be the same as that one angle. If you set two angles, well, those two angles will still be the same. However, something weird happens. In this example, we didn't put anything in the z rotation, but still, the z rotation here changes. And something even weirder happens when we set the third angle. So if all three angles are set to a non-zero value, we will notice that all of the angles will actually change. And these three angles that we input into the object are no longer the same as these three angles that the angle sensor is outputting. So what's going on here? So what's actually happening here is that the angle sensor is giving us the actual angle of the object relative to each of these axes. So these are the correct values. There's nothing wrong with the angle sensor. But then what does that imply with our three angles here that we set with the rotation of the object? Now these three angles here are what's called Euler angles. Euler angles is just a shortcut that programs use for like games or graphic displays to make it easier for humans to tell a computer how to rotate a specific object. It's designed specifically to make it easier for us to understand that like setting X would rotate it this way, setting Y would rotate it this way, and setting Z would rotate it this way. But in actuality, the actual angles of an object in 3D space is very complicated, and rotating an object in any way actually influences all of the other angles here. So for humans, it's very difficult to intuitively understand what the real angles of an object actually is. So usually if you have like any 3D graphic software or any games where you can rotate objects, they'll usually only give you the Euler angle inputs to rotate the object. Because if they allowed us to input any of these angles, it wouldn't really make sense to us. So if you're in a scenario where you need to use Euler angles, like for example, Game Builder Garage, we only have the Z, Y, and X hinges here. So the only way that we can actually rotate an object in three different axes is by doing something like this. And this is essentially the same thing that the game does with the rotation settings, where it rotates with the X first, and then the Y, and then the Z. Mathematically, the angles that you put here are not the actual angles of the object, and they're in fact just the Euler angles. They're quite different from the actual real angles of that object. So if you want to replicate the same rotation of an object, you probably can't really use the angle sensor outputs, since what we actually need to replicate a rotation are the Euler angles. Now, there is a way of converting between Euler angles into real angles and from real angles into Euler angles. In fact, the game does this all the time in its code. This is how the angles are actually stored in the game. However, the math that you need to convert from one setting to the other setting is very, very complicated and probably not recommended in any game unless that's the main goal of your game. So just to show you, I've actually replicated the equations that the game uses over here. So here I have a setup that is able to calculate, given a set of three Euler angles, so basically the three rotation settings that you set on the object, it will be able to calculate what the actual angles of the object will end up being, or basically what the outputs of the angle sensor will be. So here I have a angle sensor set to 45, 20, and -50, and it outputs these three specific outputs. And now when I put the same inputs into my calculator here, you can see that it's able to calculate all three values accurately. So the actual equations that I use here are shown here. So for example, if you want to solve for the real X rotation, first what you will need to do is to solve for these four different variables, so lowercase w, x, y, and z. So our three inputs are the capital X, Y, and Z here, which are the three Euler rotations. And you use that to solve for W, X, Y, and Z. So here, C simply means cosine and S means sine. So this is basically cosine X over 2 times cosine Y over 2 times cosine Z over 2, and so on and so forth. You solve for these four variables, which are called quaternions. Quaternions are how games actually store rotations in memory. You don't really need to know about that, but if you're curious, you can just Google that, quaternions, and dive into that deep rabbit hole if you're interested. So, but basically, once you solve for these four values, you just plug them into these equations. And then for the other way around, there's another set of equations that I've replicated here. For example, I have this angle sensor that has these outputs, these three specific outputs. And if I put these three outputs into the inputs of this calculator, what this calculator does is basically looks at these three real angles of the object and tries to reverse engineer what the three Euler angles that we use to generate it. And if we look, this is set to 42, negative 15, and 60, and we can see here that the outputs say 42, negative 15, and 60. Now, one neat thing with the existence of this calculator is you can do something like, say, you have 40, negative 10, 100 here. Let's say we want to make a angle sensor that outputs exactly 40, negative 10, and 100 in its three outputs. What we can do is put those three inputs into this calculator. Then when we look at the outputs shown here, it says 12.83, negative 24.03, and 97.26. And now you will see that the output of this angle sensor will be approximately close to what we originally wanted here. So 40, negative 10, and 100. So here I didn't put much decimal digits here. I only put up to 2 decimal digits. If you want these values to be more accurate, you can see here is already becoming a little inaccurate. You need to add a few more digits. Like for example, here instead of putting 24.03, you can put 24.02676 if you want to be more precise. And also another thing that you can notice with this calculator is that there's two number no objects here. So actually with the Euler angle system, you can actually reach the same orientation or rotation with different combinations of Euler angles. So here I'm just showing another copy here. For example, here we use a 12.83, negative 24.03, and 97.26. This other column here are actually alternative values that we can use to reach the same output. So for example, here, let's set it to negative 167.17 to negative 155.97 and negative 82.74. And you will see that it will output basically the same as before. So either of these pairs or either of these triplets would work in your case. And if you're curious what the equations I used to solve for all this, it's all laid out here. So here our inputs are the real x, real y, and real z. So this first step just calculates for x over w, y over w, and z over w, the same variables that we have in the previous equations. And here I solve for 1 over w using this equation, then using this 1 over w and these values to solve for w, x, y, and z. And then we use w, x, y, and z, as seen in these wormholes, to solve for each Euler angles. For example, for the x Euler angle, this is the equation. We use a tan 2, which is basically a position to angle nodon as well. So if you want to do an a tan 2 function in Game Boy Garage, the a tan 2 has two inputs. So there's a first input, second input. The first input you put into the bottom input of the position to angle, and the second input is the top input. You can see here, this is 2 times w times x, y times z, and this is 1 minus x squared and y squared. And here we get the Euler x. This is for Euler y. This is for Euler z. And in this game code, I've also made a shave version. And don't worry, I'll just share the game codes for these games if you want to play around with this setup. Now, one more important thing to note here is that this calculator isn't perfect, partly due to the inaccuracies of math when doing them in GBG, and also due to like specific circumstances with how the equations were formed. Certain values will result in wrong answers. For example, here I have our previous setup, which we can rotate the object depending on these inputs. And then I connected a angle sensor to that object. And then using the outputs of that angle sensor, send it through this calculator and use the outputs of the calculator to control this second object on the right. So basically what this is trying to do is to, using the angle sensor outputs of this object, recreate the Euler angles that we would need to recreate the same orientation as the original object. So here, a few of the points where this doesn't work is when y is equal to 90. So you can see here, if y is equal to 90, the rotation doesn't really make sense. That's because of weird things happening with the functions that we're using to solve for this. And also, this doesn't work if z or x is equal to exactly 180. So you can see here, it starts freaking out. And same as with x is equal to 180. But every other rotation should work fine. So with all that being said, I wouldn't really recommend using these setup and these calculations to recreate the angle of certain objects. You're probably better off using like a teleporter setup or something to recreate the rotation of a specific object. This solution takes quite a bit too much note on, and also there's also a few inconsistencies with the calculations here. I'm just showing you all of this to have a much better appreciation or understanding of how all the angles actually work in Game Builder Garage and what the angle sensor is actually doing in the background and why sometimes it doesn't really make sense to us. So that's all for this video. See you in the next one.